Good morning. Today we're going to be learning about the age of the ocean floor. So you're going to need your science journal, and if you would please put this heading on it. We'll go ahead and get started with a little bit of review of yesterday, where we learned about the mid-ocean ridges. And the mid-ocean ridges, of course, were discovered by a naval officer named Harry Hess, who was also a professor of geology at a university called Princeton. And he, and then subsequent many others, eventually mapped the mid-ocean ridges, as you did on your map yesterday too, hopefully, and you want to do that if you haven't. And they discovered that, like the seams of a baseball, they cover the entire Earth, knitting together these different fragments of the Earth's crust. And in their subsequent research, they discovered that what happens at these mid-ocean ridges is really interesting. The seafloor is being created anew by new mantle below it, rising up and pushing it apart. Here's a nice animation of that, as is this. And you can see again a plume of new mantle rock coming up. It's pushing the entire mid-ocean ridge up, and that's then creating new crust and pushing it aside. Okay, so that's just a review a little bit of what we learned yesterday. Now, in order to proceed, I would like to point out something that maybe the observant among you have noticed before if you've ever been a map gazer. I'm a bit of a map gazer, so if you are, you and I have that in common. Gazing at maps when I was young, I used to notice that there were parts of the ocean that seemed to be neither ocean nor continent, and by which I mean they seemed to be very high up, but also underwater. And so here's an example of that right off the coast of Maine. And that's actually some of our most productive fishing grounds for those of you that have fishing connections. That's the Gulf of Maine right there. And so what we call this is actually the continental shelf. And this is an interesting place where the continental crust and the oceanic crust are actually combined. Now, if you will remember back when we studied about glaciers, and we learned that there are ocean sediments that come really far inland from Maine that are from the melting of the glaciers, because as the glaciers melted, sea level rose. But the other thing that happened is that the weight of the still present glaciers also pushed the crust down, and so that caused sea level to be higher. And then I demonstrated in the stream table the gradual uplift as the ice melted, allowing the continental crust to rebound, and that then caused sea level to go down to where it is before. But I want you to understand that sea level actually, if it was to drop even more, would reveal even more of the continent's bedrock, and that would give us more land, right? So where the shoreline is now is a function of how high the oceans are, and we actually have a lot of oceanic crust that is submerged. Or sorry, continental crust that is submerged. We call that the continental shelf. So that's one thing I want to start with today, is that the continental shelf is submerged continental crust. And we're going to define that word in a minute. And attaches to oceanic crust at this area right here, these cliffs right here, and you can actually see there's these kind of underground rivers that cut right through them. Remember elevation and kinetic energy. So, and one of the things I want you to notice about at that edge is how deep it goes. And we call that the abyss. And this is actually a place where if you were swimming over it, it would the ground would, if you were to come out this way, the ground would drop beneath you and there would be nothing out there. There were some animators of a very famous movie that used this to their advantage to demonstrate the anxiety of a father whose baby fish was going to swim out over that abyss, and that is, of course, Finding Nemo. If you've ever watched that, this is that animation of them coming right out over the edge of the continental shelf and into the abyss, where it drops down literally thousands of feet in many places. So it's kind of a cool pop culture reference to the abyss. Okay, now understanding that there is continental shelf submerged, and that the actual boundary between continental crust and oceanic crust is often submerged and underwater at this continental shelf. We're going to go ahead now, and if you will please get out your vocabulary list. And if you don't have room on it, then go ahead and write on your notes. And we're going to define these two words. Start with continental crust, if you can please say that. Right. The continental crust is the thick part of Earth's crust that forms most continental bedrock. It's mostly granite, and it's too buoyant to sink into the dense mantle. And if you think about granite, do I have a piece of granite handy? Sorry, I don't. If you think about granite, you think about how light that rock is. It's got a little dark flecks in it. It's literally light in color, and that's part of the reason for that is because it doesn't have a lot of metals in the mainly quartz and feldspar that make it up, and so that actually makes it less light. And so, like a raft that's less dense and more light than the water around it, if you try to push that down into the water, it's not going to do that. And the mantle actually has a lot more dense metallic materials in it, and that is when it rises up and creates oceanic crust, it creates kind of a different animal. So if we can all say oceanic crust, right? So oceanic crust is thinner, it's more dense, and it's younger crust, making up most of the ocean floor. Okay, if you need to pause to look at that, that's fine. Now the next thing I want you to remember about what we've studied about this before is that because oceanic crust is igneous, you should remember that we can date igneous rocks. We can actually find out how old they are. And I want to remind you that radiometric dating can be used to take samples of the ocean floor and find out their ages. So yes, y'all just did this. They went out on research vessels. They drilled cores into the ocean floor. They brought up those cores, marked where they were, and then gave them to, remember the machine, the mass spectrometer, which actually measures the different ratios of daughter products to parent products in the radioactive decay. If that confused you, don't worry about it. But they basically found out the dates of these different rocks. And one of the things that's fascinating is that the findings of those surveys, so let's just quickly write that down. So geologists drilled samples from the ocean floor to find their ages. So a fascinating fact of that then is that the ages of the ocean floor are radically different than the ages of the continental crust. Okay, so they found out that oceanic crust is much younger than continental crust. So here's an example. You guys may recall that the oldest crust, the oldest rocks in the earth can be found in these things called continental shields. And here's an example of bedrock in Canada. That's 4,280 million years old. It's 4.28 billion years old. So oldest rock on continents is 4,280 million years old. Okay, so how about the rocks in the ocean? Well, this is fascinating. If you go and look at the pattern, the age of the rocks on the seafloor, you get this amazing, amazing map. And if you look at this map, so we're going to look at the scale of this map down here, and you look at all the colors on the seafloor, and I will encourage you to go ahead and look at this in more detail on your own in a minute. This scale down here starts at 0 and goes all the way up to 200 million years old. Actually, that's more than 200 million years old. But the oldest rock that we see on the oceans is 180 to 200 million years old. That's not that old. Whoops, I want it to be MYA, please. So that's a fascinating finding. And I want you to notice that the red rocks on here are the youngest, and these yellow lines, of course, you recognize that pattern because that's the mid-ocean ridges. So right around the mid-ocean ridges are these mirrored images, these stripes of rock, kind of like these stripes are being shown right here, that each rock that is being formed at the same time is going to be of the same corresponding age. So if you look at the pattern of rock age coming away from the mid-Atlantic ridge and the other mid-ocean ridges, then you find that I'm having a hard time moving this around. There we go. And you find that on either side of the mid-ocean ridges is the same amount of young rock. And I also want you to notice too that in some parts of the world, there's much more young rock on either side. And what does that tell us? Well, if you have a bigger stripe of young rock, then that suggests that these mid-ocean ridges are cranking out more rock in the same amount of time as these, because in the same amount of time that this amount of rock has been formed on either side of the mid-Atlantic ridge, in the mid-Pacific ridge, you can see this much rock has been created. So that one's really cranking. So things I want you to notice before you start actually putting this on your map is that on either side of the mid-ocean ridges is the very youngest rock in the world. And I'm going to ask you to please draw that pattern on your own map. If you've already used red for another color, then choose another color, but make sure you indicate on the key that that's your youngest rock. And the farthest away from the mid-ocean ridges is the oldest rock, and this cyan color, which again, if we look at the scale down here, and you would have to kind of zoom in to really see it, is 180 to 200 million years old. So earlier I was saying that your oldest on here is actually, it's 280 million years old. But again, none of the ocean floor is that. Those 280 million year old rocks are on the continental shelf. So that is really interesting. And I want you to add that as your last notes here, is that the youngest rocks are closest to the mid-ocean ridges and mirror images of each other. And the oldest rock is at the boundary between the continental and oceanic crust. That's pretty cool. That's a pretty neat discovery. And so now I'm going to ask you to please add that information to your map. So again, I want you to color in the youngest rock in the oceanic crust on your blank world map. And ideally that would be red. If you've already used red, use another color and indicate what it is on the key. And your oldest rock, I would like you also to color in where that is on your map of the world. Thank you very much for listening.